Okay. Okay, so we have this problem. I'm going to solve this rather quickly. And the point I want to make here is we're probably going to get two solutions out of this. And if we get two solutions, we've got to check them both. As a matter of fact, we just got one solution. We really want to check it because it's possible that at least one of those solutions might give you a negative under the radical. So that's entirely possible when you start squaring both sides. Okay. Now, I think you said that's supposed to be 39. Okay. So let's get change to 34 to 30. And that's going to change the 56 to 61. Okay, so I'll make those changes in a minute. So there's a ink drive. Okay, so this is 39. This should be 39. This is 39. And that's going to make this, just double check. It should be 61, but let's be sure. Yeah, 39 and 32, 61. Okay, so I think I've got it. Now, does this agree? That's what you've got so far. Okay. Then we square both sides of this. So I'm just going to do that in one step. You really ought to be writing out both steps. Okay. So when I square all this, I'm going to get 4 times negative 24x minus 39 times negative 32x minus 60. And that's going to equal the square of this. Okay. Now 61 squared, everybody knows, is 3,721. Okay. So yeah, we start getting some big numbers here. Okay. You get 3,721 when you square that? Say yes or no. Okay, shake your head. Okay, let's see what you got because I did it in my head quickly. We got 56 next here. Okay. But you got a minus 39. Oh, you had a 60 on the, yeah, there is a 60. Okay. There's negative 32x. Okay, let's make sure we got the numbers right. We have a negative 24x. Oh. This is what needs to be increased by 5. So let's erase this, get it straight. We do get a 56x, which we had before. When we change this number, that changes this number and this number, which gives us 99, and then we add 1 and we get 100. Well, that should agree. Okay. Now 56 squared is 2,500 and 600 is 100, 31. 36x plus 5,600. 11 times 200. That's the next. Plus 10,000. We in agreement? Doing these things in my head. Okay, so if we're in agreement here, then we're probably right. All right. Well, now I've got to multiply out everything on this side. And we have 32 times 24. Well, I'm going to pause the video. You don't need to have a video with me fumbling around with the numbers. Okay, I actually had to resort to asking to do this with a calculator. But I think maybe these are the right numbers. They all make sense. But I just don't have the working memory, at least not this morning, and probably not pretty much any time to reliably accurately do those in my head. The rest of it is pretty easy. If I subtract 3072 from 3136, I get 64. So I'm going to bring it over on this side. So I've got 64x squared, and then 10,800 from 11,200 is 400, so that's going to be 448. And then 640 equals 0. Now at this point, I want my number to get smaller. Okay, so I'm going to divide by, can I divide by 8? Yeah, I can divide by 8. Can I divide by 16? Yeah. Yeah, divide by 16. At least divide by 16, which would give me 4x squared plus 30 less 2 is 28 x plus 40 equals 0, and I can still divide by 4, which is going to give me x squared plus 7x plus 10 equals 0. Okay. So you divide by 4, you divide by 16, then you divide by 4. And I could have tried dividing by 64, because 64 goes into this as well as this. And I really didn't want to divide that by 64, because again, it's quicker for me to divide there and then divide by 4. And it's more reliable. So I'm still not sure I got it right. But the problem with this is that I don't appear to get any solutions, because my discriminant is going to be b squared is going to be 49, then you got to multiply. Oh, wait a minute. 49. Never mind. Why? Okay, so we get -7 plus the square root of 9 over 2. So with all those numbers, the fact that it appears to have come out to result with a squared discriminant where we can get exact solutions leads me to believe that might be right. Okay, it's unlikely, if I made a mistake here, it would come out that nicely. And I conjecture that open math intentionally made it nice. So you go through all this agony here. Now, another thing that I should have noticed is I have a common factor 4 between both sides here, for sure. Okay. And then I'm going to get more factors of 4. So I could have divided through by 4 at this point, which would have given me smaller numbers that I probably could have done accurately in my head. At least I'd have had a 70% chance, maybe, depending on the day. So if you spot something like even what you get here, well, if you divide both sides by 4, it's clear that all these numbers are going to divide by 4. Actually, no, because that one probably doesn't. Anyhow, okay. Keep that trick in mind. You can simplify your numbers a whole lot. But I tried to plug these numbers in and square this one and do this one times this one, which would have been pretty easy because over the powers of 2 times 5. Okay. All that aside, -7 plus 3 is -4, so we get -2. -7 minus 9 is -10. You get -5. It's -7 plus or minus 3 over 2. So that's very straightforward. So the question is -2 a solution to this equation? Is -5 actually a solution to this equation? If x is -2, then we get 48 here minus 39. And that's fine. Okay. And if x is -2 here, we get 64 minus 60, and that's fine. And of course, 48 minus 39 is 9, so we have the square root of 9. And this gives us 2. Square root of 9 minus the square root of 4 is 9 minus 2 is 3 minus 2, which is 1. Okay, and it checks. So that makes it even more likely that we actually got the numbers right. And well, what about -5? So -5 gives us 120. 120 minus 39 is 81. Square root of 81 is 9. And -5 times -32 is 160. 164, subtract 60, you get 104. Wait a minute. It's 160. Okay, no, okay. It's nine minus 10. Okay. Now the original equation didn't have the squares on here. The original equation was okay, so you can do the substitution. It's real easy. Substitute x equals 2, you're going to get 1 equals 1. But if you substitute x equals -5, you get -1 equals 1. That's not okay. So the only solution is x equals -2. What happened was when you squared both sides, well, -5 satisfies this equation because what's inside the parentheses gives you -1. When you square it, you got 1. Okay, so -5 does satisfy this equation, but it doesn't satisfy this because the left-hand side, when x equals -5 is -1. If you square -1 equals 1, you get 1 equals 1, and everything is good. So the lesson is that you verify your solutions. Something you always want to do anyway. But this would be the first instance you've probably seen of something that looks like it ought to be a solution, but turns out not to be. When you square both sides of an equation, you can get extraneous solutions. Of course, you always want to verify your solutions anyway. And if you find an apparent solution that doesn't work, you just eliminate it. Okay. Okay, so again, I want to reiterate, we're talking a little bit about, the fact of the big numbers, and you make one little mistake, just one clerical mistake, you put down a 2 instead of a 4 or something, and you don't get a nice solution like this. And that's why we wanted to be really careful with all these numbers, okay? As I said, when everything got down to this point, actually, at this point, it's very clear that you could divide both sides of this equation by 2, right? And if you divide both sides by 2, then you can look at it again. All the numbers are still, even if you have an even factor, well, you can divide by 4. And you might even look at, since you've got a 4 out here, divide everything by 4, the numbers get a lot smaller. Okay, you lose a digit on just about all of these numbers. And then when you get it down to this form, again, look for common factors, because if you look at the common factors, you could have divided by 4 here. You could have divided by 2 here, and then you could have divided by 2, and then you could have divided by 2, then you could have divided by 2, and then you could have divided by 2. Maybe once more, I kind of lost track. Okay, you divide by 2 6 times to get from here to here. It's always easy to divide by 2. Or you can take a stab and try to divide by 4. Okay. Okay, well, let's look at the pendulum problem. I'm going to pause for a second. Okay, so we have another problem that arises. E equals 2 pi squared of L over G. Okay. Period of a pendulum, and L is the length, and G is the acceleration of gravity. Okay. Now you can plug the given numbers into this equation and get a good solution if you do all the steps right. Now, looking at the steps, because this came up as a question, I don't really see what's wrong with the steps, but the answer came out way too high. This pendulum is about 160 feet long, and a 160-foot pendulum, believe me, takes more than 1.3 seconds to oscillate. Okay. And of course, you can take that back and check it. If you put that answer, that 50 meters or so, in here, divide by 9.8, which is your acceleration of gravity, you're going to get like 15 over here, okay? And the square root's going to be, well, square root of 16 is 4, so that's going to be around 4, and you multiply that by 2 pi, which is around 6, and you get around 25. So it'll be around 25 seconds, the pendulum of the length you got doing this thing with the numbers, okay? And I still don't see what you did wrong, but yeah, just what I'm looking at it. We're going to solve for L because the problem gives you the period and asks you to figure out the length. And so I'm going to get, well, you have the right instinct to square both sides. So T squared is going to be 4 pi squared L over G. Just squaring the 2 pi. Not putting any numbers into it at this point. Then get a place to put my feet here. Okay. Then we're going to solve for L. Okay. So what we can do multiply both sides by G over 4 pi squared. And that's going to divide out the 4 pi squared, going to divide out the G. And we get L equals, we can write it this one expression, GT squared over 4 pi squared. And now we can substitute the numbers. So let's say I'm not going to use the same number you got, but I'm going to say, let's say t was 1.4 seconds. Okay. Now I'm going to stick my neck out. When I got that pendulum over there, it just happened to be hanging there, and it's still oscillating. 1,001, 2. Okay, and I'm thinking it's pretty close to 1.4, 1.5 seconds. Okay, so I'm going to use 1.4. So G is 9.8 times 1.4 squared over 4 pi squared. Well, if you do that, 1.4 squared is close to 2. 4 pi squared is close to 40. So you get like 2 over 40 times 9.8. That's like 20 over 40. You do the numbers, but that comes out approximately 0.5. And it's pretty close to that. I don't think it's off by more than 5%. Okay, now I'm going to take a meter stick and I'm going to measure that pendulum to see if my estimate of the period was any blame good. Okay, just hanging there, using physics, knock my head on it every once in a while. Look at that. That's 50 centimeters right there. Okay. Thumbs up or thumbs down if you agree that was really 50, not 49 or 51. Okay. So my estimate of 1.4 seconds is looking pretty good. We could time it. You know, I've just got to do that. Okay, now of course I teach physics, so I've been counting 1,001, 1,002 stuff for a long time. And some days my seconds are just about right. And what I counted there turns out to have been just about right. I counted 7 cycles in 10 seconds, which is 1.42 seconds, 1.43. And, you know, even on days when I can't do any arithmetic in my head like today, sometimes my ability to count seconds is just fine. And some days when I can do the arithmetic, my ability to count seconds isn't. And I think it would be really interesting to do an experiment. You know, just make myself do some random arithmetic, see how well I do in my head, and then count the seconds or something. And see if there's an inverse correlation between my ability to count seconds and my ability to do mental arithmetic. It'd be interesting, but I'm probably not going to do it just for sake of time, but I might. I'd have to take a little time to set it up, but it wouldn't take long.